Welcome everyone to Science 110. This is Electricity and Magnetism. I am Professor Brennan Brown, and today we will be exploring the fundamental principles of electrical energy here at Sandhills Community College. By the end of this session, you should have a firm grasp on the forces that govern charge, how that charge moves, and how we harness it for practical use. So, we're going to begin with the concept of electric charge. It is essentially a fundamental physical property of matter, meaning it's something that just is in matter and it just exists there. You can think of it as an intrinsic quality, just like mass. Like nothing gives particles mass, they just have mass. It's something that we've defined and see or observe in matter. This particular intrinsic property just causes some particles to attract or repel one another. All of the electric charge that we encounter in the universe ultimately originates in the subatomic particles that we learned about in the chemistry section, that is, the protons and the electrons. Protons are particles that carry positive electric charge, and electrons are particles that carry negative electric charge. That's really kind of an arbitrary distinction. There's nothing special about positive or negative. It's just that they're opposites of one another, and we wanted a way to describe the opposite nature of these charges. So one got called the negative charge and one got called the positive charge, and here we are today. When these charges come close to one another, they exert an electric force. This is the force of attraction or repulsion between any two charged particles. It follows a very predictable pattern. Particles with opposite charges, like protons and electrons, they attract one another. Conversely, particles with the same charge, like two protons or two electrons, they repel one another. This interaction is the push and pull that forms the basis for everything we're going to discuss further in this presentation. It's how we manipulate electric charges and get them to do useful things that we want them to do. So we know that charges can push and pull on each other without even touching, but how does one object know the other is even there if they don't make physical contact? This is where the concept of the electric field comes in. To make this less abstract, I want you to imagine an invisible influence zone or bubble around every charged particle. Think of it like a magnet sitting on a desk. If you move a paperclip near the magnet, you can feel that invisible tug before they actually click together. The space where you feel that tug, that is the field. Electric fields work the same way. Every charged particle creates this invisible bubble of influence around itself. When the two particles get close enough that their bubbles overlap, they start to interact. If you put another charged particle in that bubble, it immediately feels the push or the pull from the first particle. So we don't need to imagine these particles reaching out and grabbing each other. Instead, we can think of them as constantly changing the space around them. The field is simply the map of that influence. It's how one particle tells another particle, hey, you should move this way, without ever having to touch it. I like to think of it as like a topographic map sometimes, where you can see hills and valleys like in a real topographic map. You can see hills and valleys of charges using these electric fields. Now we need to talk about one of the most important rules of the road in physics, the law of conservation of charge. Think of the universe like a giant accounting system. Electrical charge isn't something that can just pop into existence out of nowhere, and it can't disappear into thin air. It is always accounted for. If you have a certain amount of positive and negative charge in a closed room, that total number stays exactly the same no matter how much you move things around. You can shift charge from one object to another, but you were only ever moving what was already there. To understand how all of this moving around happens, we look at how different materials handle these charges. We group them into two main categories. Conductors you can imagine as a busy hallway where students can run freely. These are materials like copper or gold, where electrons are loosely held and can zip around with almost no resistance. They are like highways for electricity. Now imagine the same hallway, but it's packed with furniture and obstacles. These are materials like rubber, glass, or plastic. These are called insulators. Electrons are stuck in place and really struggle to make their way through these types of materials. They act more like a roadblock rather than a highway, keeping charges contained where they are. So when we talk about electricity in our daily lives, we are almost always talking about moving charge through conductors while using insulators to keep that flow contained and safe in spaces where we want it to be. So now we've talked about what charge is and where it lives, but how do we actually get it to move from point A to point B? Since charge is conserved, remember we aren't creating new charges, just shifting what's already there. There are three main ways we can cause that shift. The first is friction. This is the rubbing method. When you rub two different insulating materials together, it's like physically scraping the electrons off of one surface and depositing them onto the other. This is why you get that zap when you rub a balloon on your hair or drag your socks across a thick carpet. You are literally peeling electrons away and building up an imbalance on the surface. Second is conduction. This is the direct contact method. If you have a charged object and you touch it to a neutral conductor, the electrons will naturally spread out to balance themselves. Think of it like a crowded room opening a door into an empty one. The people, or in this case the electrons, will flow into the empty space to find a more comfortable balance. Third is polarization. This one is a bit like a game of follow the leader without the touching. If you bring a highly charged object near a neutral material, it doesn't necessarily touch it, but it exerts a force that shifts the electrons inside the material. The electrons are pushed to one side or pulled to the other, creating a temporary positive end and negative end within the material that was neutral just a few seconds earlier. It's like rearranging the furniture in the room just by standing at the door. To understand the world of electricity, we first have to look at what happens when charge stops moving entirely. Static electricity is charge that has built up on the surface of an object and is sitting still, waiting for an opportunity to move. In our daily lives, we often encounter this when we feel a sudden sharp snap after walking across a carpet and touching a doorknob. This is what happens because the materials we interact with, our shoes, the flooring, or even the clothes we wear, are often insulators. Because these materials resist the flow of charge, electrons become trapped on the surface, unable to move through the material to neutralize themselves. Think of it like a bucket being filled with water. The water is stored there, but it is not currently flowing or doing any work. It just stays concentrated in one area, the bucket, creating an imbalance. This stored energy is just waiting for some path to equalize. The release happens when that stored up energy finds a path to escape. If you bring that accumulated charge near a conductive material like a metal doorknob, the electrons find that highway to travel out on. They dump out all at once to get back to a balanced state. That rapid, instantaneous, sudden release is what we call a static discharge. It's the same principle behind a lightning strike, which is what nature's way of equalizing massive buildup of charge between the atmosphere and the ground. The clouds, through friction, build up an immense amount of static charge, and once the air can no longer hold that charge back, it discharges through the air to the ground in a big, bright, brilliant flash of static electricity. To make the energy we have been discussing actually useful, we have to move beyond stationary charge and find a way to create a steady, continuous stream of charge. This continuous movement is what we refer to as electric current. Think of the difference between a stagnant pond and a flowing river. Static electricity is like that pond. It has potential, but it's just sitting still. If you want to power something like a water wheel or something like that, you need that charge to start moving. You need that water to start moving. So if you want to power a computer or a motor or something like that, you need to get that current moving, just like the water in a river can turn the water wheel. When we talk about current, we are essentially looking at the flow rate. We measure it by counting how much charge, specifically how many electrons, pass a single point in a wire over a specific amount of time. The standard unit we use for this measurement is the ampere, which is most often just called an amp, and represented by the capital letter A. So whenever you see an amperage rating on a household appliance, that number is simply telling you how much charge needs to be flowing through that device every second for it to operate at its intended level. To understand what actually drives the movement of charge through a circuit, we have to look past the wires themselves and focus on the force that initiates the flow. Electrons do not spontaneously migrate through a conductor. They require a deliberate push, which we call electric potential, or more commonly, voltage. To visualize this concept, it helps to think in terms of gravitational energy. Imagine a ball perched at the top of a steep hill. Because of its position, it possesses a high amount of potential energy, and it naturally wants to roll down to the bottom where the potential energy is lower. Electricity behaves in an identical fashion. Electrons act like that ball, naturally seeking to move from a location of high electric potential to a location of lower electric potential. Voltage is essentially the measurement of that potential energy difference between the two distinct points in a circuit. If you have 2 points that are at the exact same potential, there is no slope for the electrons to slide down, and consequently, no current will flow. This is why every electrical device needs a source, like a battery or an outlet, to create this artificial height difference. When you plug a device into a standard wall outlet, you are essentially creating a pathway that creates a high potential source to a lower potential destination. That 120 volt rating that you see on your devices represents the specific amount of potential energy difference available to push those electrons through the internal circuitry, providing the necessary energy for the device to perform its work. Electric current can travel in two distinct ways: direct current and alternating current. Direct current is a steady one-directional flow, which is the standard for things like battery-powered devices, including smartphones and flashlights, because as you can see from the diagram here, the current flows consistently from the source to the load. Alternating current, however, rapidly and continuously reverses the direction of the electron flow. This is the standard for our national power grid because it allows for high efficiency voltage transformation, enabling us to transmit power across hundreds of miles from power plants to your home with minimal energy loss. Because alternating current reverses direction so rapidly, typically 60 times a second in the US, it creates oscillating magnetic fields that allow transformers to change voltages easily. Direct current is easier to store in batteries, but difficult to transport over long distances. This is why alternating current is the current that we use in our power lines. Resistance is the opposing force that works against the movement of electric current. Measured in ohms, it acts as a form of electric friction that slows down the flow of electrons as they attempt to pass through a material. The resistance is not just an obstacle. It is often a functional component of a device. When electrons collide with the atoms inside a resistor, like the filament in a light bulb or the coils in a toaster, the electrical energy is converted into heat or light, allowing us to perform useful work. Every material has an inherent resistance, depending on its atomic structure. By selecting materials with specific resistive properties, we can create heating elements, light sources, or signal regulators. Managing resistance is essential for efficiency. In our power lines, we want as little resistance as possible to avoid losing energy as heat during transmission. The level of resistance in a material is determined by three variables: length, width, and temperature. A longer wire increases resistance because the electrons must navigate more atomic collisions. A wider wire provides a larger path, decreasing resistance, much like a wider pipe allows more water to flow. Temperature also plays a critical role. In most materials, as the temperature rises, the atoms within the wire begin to vibrate more rapidly. These increased vibrations create more obstacles for the moving electrons, effectively increasing the material's resistance to current flow. Engineers must account for these factors when designing electrical systems. For example, long-distance power lines are made as thick as possible to reduce resistance and keep away from heat sources. Understanding these physical limits is key to building systems that are both effective and safe for long-term use. The fundamental relationship between voltage, current, and resistance is defined by Ohm's law. This law states that the current in a circuit is directly proportional to the voltage applied and inversely proportional to the resistance of the circuit. This simple mathematical relationship, current equals voltage divided by resistance, is the primary tool for all electrical engineering. By mastering this equation, you can calculate exactly how much power will flow through any circuit, ensuring that every component receives the right amount of electricity without overloading. Ohm's law is the secret to troubleshooting. If you know the voltage and the expected current, you can calculate what the resistance should be, which allows you to identify faulty wires or damaged components. It is the bedrock upon which all electrical design and diagnostics are built. To truly understand these concepts, we must apply them to real-world scenarios. Through the following practice problems, we will look at devices like toasters, chargers, and motors to see how changing resistance or voltage directly impacts current. Each scenario reinforces the mathematical link between these three variables. These problems are not just academic exercises. They represent the same calculations a technician performs when troubleshooting a malfunctioning device. By solving for unknown variables, we learn how to balance the demands of modern electronics and ensure our circuits operate safely. Whether it is calculating the load on a toaster or the resistance of an electric bike motor, these problems teach us how to think like electrical engineers. They provide the practical experience needed to trust our designs and understand how electricity behaves under different loads. We can see some practice with Ohm's law here on this slide. We learned on the previous slide that the formula for Ohm's law says that amps is equal to voltage divided by resistance. Now, just so you know, sometimes when you see this in other textbooks, amps is replaced with the letter I, just to represent amps in the formula. I'll leave it like this to avoid any confusion. So, the current in an electrical device is equal to its voltage divided by its resistance. So in the case of our toaster here, the problem says you are making breakfast and your toaster, which has a resistance of 12 ohms, is plugged into a 120 volt outlet. How many amps of current are flowing through the toaster's heating coils? We can see from the problem here that amps is equal to the fact that the toaster has 120 volts and a resistance of 12 ohms. Now this is a pretty straightforward problem. We can see that 120 divided by 12 will tell us how many amps of current are flowing through the toaster. And of course, 120 divided by 12 is 10. So our toaster has a current of 10 amps. On this slide, we can see we are asked to use the Ohm's law formula again, but this time in a little bit different manner. We're being asked to solve for volts instead of for amps. The problem reads, your smartphone battery charger is pushing a current of 2 amps into your phone. Since the formula for Ohm's law says that amps is equal to voltage divided by resistance, we may want to go ahead and plug in 2 for the amps. If the internal resistance of the phone's charging circuit is 3 ohms, how many volts is the charger providing? So we don't know V, but we do know that the resistance is 3 ohms. Now we have a little bit of algebra to do to solve for V to determine how many volts the charger is providing. To solve a problem that looks like this with the unknown in the numerator and known values in the denominator, we will multiply both sides by that denominator. Multiply both sides by 3. This will cancel the 3 here. 3 times 2 is 6. So the number of volts that the charger is providing is 6 volts of electrical potential. Here in our last example, we can see we're going to be asked to solve for resistance given the voltage and the amperage. The problem reads, you are riding an electric bike that uses a 48 volt battery. If the motor pulls 6 amps of current while you are riding uphill, what is the total resistance of the motor system? So as we said before, A is going to be equal to the volts divided by the resistance. And in this case, we don't know the resistance. We do know the amperage and the volts. So we have 6 amps as the total power being used across an electrical potential of 48 volts. We don't know R, so that's what we're going to try to solve for. If we paid attention in algebra, we learned that we have a problem where the unknown is in the denominator. We can switch what is on the other side of the equal sign with the denominator, and that will tell us the answer. So in this case, R is going to be equal to 48 volts divided by 6 amps. And 48 divided by 6 is, of course, 8. So the resistance of our bicycle is 8 ohms. Here is our next example, which reads, you are testing a string of decorative lights. You know the string has a resistance of 100 ohms, and you notice that 1.2 amps of current is flowing through the wire. What is the total voltage across this circuit? So again, we're going to use Ohm's law, which states that the amperage of an electrical circuit is equal to its voltage divided by the resistance. And in this case, we know we have 1.2 amps of current flowing into our lights. We are being asked to figure out the supplied voltage to get that power into the lights. And we've been told that the whole circuit has a resistance of 100 ohms. So like we said before, if we remember back to our algebra classes, we solve this type of problem by multiplying both sides by what's in that denominator. So I'm going to multiply both sides by 100. 100 will cancel on this side. Since we have one on the top and one on the bottom, it divides out to 1 and cancels itself out. On the other side of the equal sign, 100 times 1.2 is going to be 120. So 120 volts is the volts that are being supplied for this particular string of lights, which probably means it's plugged into a wall outlet because that's the standard voltage of most wall outlets in the United States. Here we have our last example, which reads, a small desk fan is plugged into a 12 volt power supply. The fan's motor has a resistance of 8 ohms. How much current is the fan drawing? So again, we remember that amps is equal to volts divided by resistance. And in this case, we're being asked to solve directly for amps. Pretty easy problem here. And we know that the power supply for the fan provides an electrical potential of 12 volts. We know that the fan assembly has a resistance of 8 ohms. And so to solve for amps, we need to simply divide 12 by 8. And 12 divided by 8 is going to be 1.5. So there is 1.5 amps of current powering our desktop fan. An electrical circuit is a closed loop designed to provide a continuous controlled path for electric current. For a circuit to function, it must have a clear path from the voltage source through the load, which does the work, and back to the voltage source to complete the loop. If this path is ever interrupted, for example by a broken wire or an open switch, The circuit becomes open and the flow of electrons stops immediately. A functioning circuit requires the perfect, unbroken loop to maintain the flow of energy required to power our devices. Designers spend significant time creating these loops, ensuring that the path of electricity is robust and reliable. From the simple wiring of a flashlight to the massive integrated circuits in a smartphone, the fundamental requirement remains the same. This loop must be closed for the energy to flow. Because drawing every battery and resistor as a literal object is impractical, we use circuit diagrams. These diagrams use a standardized set of symbols to represent components, making them a universal language for engineers and electricians around the world. By learning these symbols, you can quickly interpret the design of any electrical system. Whether you're looking at a simple flashlight circuit or a complex computer motherboard, these diagrams show you exactly how electricity is meant to travel, where the switches are, and how the loads are connected. These schematics are essentially the architectural blueprints of the electronics world. Without these standardized symbols, it would be impossible to collaborate on complex designs or safely perform repairs, as every device would require its own unique, non-transferable set of instructions. Circuits are generally arranged in one of two configurations, series or parallel. In a series circuit, all components are connected in a single path, meaning that if one component fails or a connection is broken, the entire circuit loses power. Parallel circuits, on the other hand, are designed with multiple independent loops. If one branch of a parallel circuit is interrupted, the electricity continues to flow through the other branches. This is why your home is wired in parallel. You can turn off one light without causing every other appliance and light in the house to stop working. Selecting the right circuit type is crucial for system design. Series circuits are great for simple devices or for creating one single control point, while parallel circuits are necessary for building robust systems where reliability and independence are key. Knowing how to combine these layouts allows for the creation of incredibly sophisticated electronic environments. We've just spent plenty of time in our presentation talking about electricity, the flow of electrons through wires and the power that runs our devices. But there is a cousin to electricity that you've likely interacted with since you were a kid playing with refrigerator magnets. Now we're going to introduce magnetism. It's a force that, like gravity, we cannot see directly, but we can see its effects everywhere, from the compass in your phone to the very core of our planet. While electricity and magnetism might feel like two separate topics, they are actually deeply intertwined. Think of electricity as the result of electric charges being present, while magnetism is essentially what happens when those same charges start moving. Because our modern world relies on this relationship to generate power and store data, understanding how a simple magnet functions is the first step in seeing how our most advanced technology actually works. Magnetism is a force exerted by magnets on specific materials, such as iron, cobalt, and nickel. Every magnet, regardless of its size, is defined by having two poles, a north pole and a south pole, which are the regions where the magnetic field is most intense. Crucially, these poles are inseparable. If you were to take a magnet and cut it in half, you would not isolate a north pole or a south pole. Instead, you would simply create two smaller magnets, each with its own north pole and south pole. This fundamental property is what makes magnetic fields so predictable and useful for navigation and engineering. Magnetism has been a source of fascination and utility for centuries. From the earliest compasses, which relied on Earth's natural magnetic field, to the high-tech magnets in modern medical imaging machines, we have harnessed this force to do everything from guide ships to peer inside the human body. A magnetic field is the invisible zone of influence surrounding a magnet where the magnetic force is active. This field follows rules that mirror the behavior of electric fields. Opposite poles, north and south, are magnetically attracted to one another, while like poles will repel each other with significant force. These fields are not merely theoretical, they are the mechanism by which magnets interact with the world. By understanding the geometry of these fields, we can create complex devices that use magnetic force to perform physical tasks, such as spinning a motor or lifting heavy metallic objects. Engineers use field lines to visualize how these forces will behave, ensuring that magnets are oriented correctly for maximum effect. Whether we are aligning a magnet inside a speaker to create sound or guiding the movement of a high-speed train, it is the manipulation of these invisible fields that makes the technology work. Magnetism is the specific ability of a material to be attracted by a magnet or to function as one. While most substances do not react to magnetic fields, materials like iron, cobalt, and nickel have internal domains that can align to create a magnetic effect. These materials can be magnetized by coming into contact with a strong magnetic field, which forces their internal domains into alignment. Conversely, they can also be demagnetized, losing their magnetic properties if they are exposed to intense heat or a sudden powerful physical impact, both of which cause their internal domains to fall back into a disordered non-magnetic state. This sensitivity is how we store data on magnetic media like hard drives. By precisely flipping the magnetic state of tiny domains, we can record binary information. Understanding how to control and preserve these magnetic states is the foundation of our entire digital storage infrastructure, demonstrating the incredible versatility of magnetic materials. To conclude our review, it is clear that electricity and magnetism are not separate phenomena. They are two deeply intertwined sides of the same coin. From the controlled flow of current that powers your phone to the massive magnetic fields that generate the electricity we use every day, these forces form the framework of our modern world. Understanding these principles allows us to harness the power of nature to solve human problems. Whether we are discussing the simple flow of charge in a battery or the complex engineering of a power plant, these fundamental concepts remain the key to our technological progress. Thank you for joining me today. As you go forward, I encourage you to look at the devices in your home and consider the invisible fields and electron flows that allow them to function. Mastery of electricity and magnetism is the first step toward understanding the mechanical and digital marvels of our age.